Okay, so we are moving into the last question. So question number 5. Right, this is very, very straightforward, I would say. So a titration between the monoacidic base B. So let's do like this. So we have B here. No, so it's the other way around. So they are taking HCl into the flask. That is the normal way. So HCl concentration is 0.1 m, and they have taken 25 cubic centimeter, and they are going to titrate with the base, okay, B, that is 0.15. concentration is little bit different. HCl solution kept in the titration flask. Okay, weak base is added using the burette, right? Okay, Kb is given. Kb for the weak base is given as 1 into 10 to the power minus 5. Like the Ka, they have also given the Kb. 25 degrees Celsius, all experiments were conducted in 25. So calculate the pH of the initial solution. So pH is very easy. Now this part is very easy, right? Because you know pH is equal to minus log H plus concentration. So you can write down minus log 0.1 m. So basically pH would be equal to 1.0. Calculate the pH of the solution in the titration flask after addition 10 cubic centimeter of solution B. So think about this. Basically what is going to happen? B plus HCl going to form the salt plus water. Okay. The stoichiometry will be always 1:1 because this is a monoacidic weak base, right? So you will have here 0.15 times 10 cubic centimeter is added. So 10 into 10 to the power minus 3. Then in the titration flask, you have 25 into 10 to the power minus 3 times 0.1 m. Okay, the amount of moles of HCl here is now initial moles. Anyway, it is 2.5 into 10 to the power minus 3, right? So you are adding 1.5 into 10 to the power minus 3 moles, right? So what is going to happen? You see here, B is limiting, HCl is excess. So basically, B is going to completely react. So no B will be remain. But HCl is 2.5 minus 1.5 into 10 to the power minus 3, because now that is the remaining amount will be 1 into 10 to the power minus 3. So HCl will be remain 1 into 10 to the power minus 3 moles. B will be nothing. So the same amount of salt will be formed, right? Because reacting amount will be formed. So basically salt will form 1.5 into 10 to the power minus 3 moles. This is the idea. So you can find the concentration by dividing this by the volume. So total volume should be 25 plus 10, 35. So if they say to find the concentration here, you need to find the concentration by divided by 35 into 10 to the power minus 3 decimeter for the remaining acid. And for the salt, if they ask about the salt, 10 to the power minus 3 decimeter. Okay. So they say calculate the pH. Yes, they say to calculate the pH. So at the end of the 10 cubic centimeter, you will not find this weak base. Okay. You will only find in the solution the strong acid as well as the weakly acidic salt. Okay. So from these two, when you have a strong acid remaining in the solution, we omit the salt to calculate the pH. So we will go only with this one. So basically 1 into 10 to the power minus 3 divided by 35 into 10 to the power minus 3. So I can cut this one to cut this one. So 1 over 35 will be the concentration. So it will be quickly. I will go through the yeah. 1/35 is 0.028. So this will be 0.028. And when you calculate the pH based on this concentration, it will be around 1.6. Okay, this is done. And they are asking an additional question. Can the solution in the titration flask act as a buffer solution? Explain your reason. So to act as a buffer solution, you need the weak base as well as the salt of this weak base. But here you see only the salt is remaining. So here it cannot act as a buffer solution. So that is the reason as well. Calculate the volume of the weak base solution required to reach the equivalence point. So to reach the equivalence point mean mole of this should be equal to mole of this. So basically you can write down to reach the equivalence point, you can write down a statement like to reach the equivalence point, moles of B should be equal to moles of HCl. So moles of B means it is 0.15 m times the added volume, we don't know the volume, should be equal to 0.1 m times 25 cubic centimeter. So this would be the volume. So you calculate the volume, you will end up with getting like something like 16.67 cubic centimeter. Okay, so this is the way. Because the stoichiometry is 1:1. So the same amount of mole should react. Okay. Next one, another 100 cubic centimeter of volume of weak base was added to the titration flask after reaching the equivalence point. Calculate the pH of the solution in the titration flask. So what they are telling here. So when the equivalence point is reached, you have added 16 point something. Okay. So at the equivalence point, there will be only this salt. Okay. And what they do is add another 10 cubic centimeter of the weak base. So now in this solution, what do you have at the after the equivalence point? So after the equivalence point, you have the salt plus the weak base. So basically now this is a buffer solution. Okay. They have asked, can the solution in 4B act as a buffer solution? Yes, it should be, because you have the weak salt and the weak base here. So this will act as a basic buffer. Okay. So this will act as the buffer. In fact, this will act as the buffer. So what is happening here? Basically, when you have this B plus HCl reaction at the equivalence point, you will have only the salt. So how much will be there at the equivalence point? The amount of salt, it will be equal to the number of moles of B and HCl. So it will be 2.5 into 10 to the power minus 3 moles will be there. Why? Because 1:1 reaction will give 1:1 salt. So if you have the 2.5 into 10 to the power minus 3 moles of B, you have 2.5 minus 10 to the power minus 3 of HCl. So salt is going to form, same amount is going to form for the salt. So if you have this amount of salt, then what they do? They add 10 cubic centimeter of the base again. So what is the amount of base? Now the base amount is 0.15 into 10 to the power minus 3. What is the volume? 10. 10 into 10 to the power minus 3. So now you know the amount of the weak base present. You know the amount of the weak salt present. So you can divide it by the volume to get the concentration. Now the total volume should be, remember, here there is 25 initially in the flask. To get the equivalence point, we have to add this amount, 16.67. So the total volume will be 25 plus 16.66 plus the additionally added 10 cubic centimeter also should be there. So 10, all 10 to the power minus 3. Okay, so here also that should be the volume, right? But we don't have much of a problem of the volume, but I want to tell you this is the total volume, right? Because this is a buffer solution. To calculate the pH, you can directly go to the Henderson equation. pH is equal to pKb log the salt concentration over the base concentration, right? So pKb you can directly calculate from the Kb value that is given 1 into the power 5 minus log 1 unit in the power 5 means this will be 5.0. And log of the salt concentration divided by buffer concentration means this concentration divided by this. So this thing to this thing going to cancel out. 10 to the power minus 3 to 10 to the power minus 3 is going to cancel out. So it will be 2.5 divided by 1.5. Okay, it would be 2.5 divided by 1.5, and its log value is 0.221. Okay, here, sorry, it is POH. I forgot. So this POH would be 5.221. So from pH equation, where pH is equal to 14 minus 5.221, you can calculate the pH as 8 point something. Okay, get the idea what we have done. We first consider the total salt amount form, that is 2.5 into 10 to the power minus 3, and additional amount 0.5 into 10 to the power minus 3, and then we calculate the concentration, and you plug into POH equation, then find POH, then find pH. That's the idea. Next question, escape the variation of the pH mixture in the titration flask with the volume of the weak base solution added and label the axis. Indicate the pH on the y-axis and the volume of the weak base solution in the north. Mark the equivalence point approximately. So basically, it is like this, right? So you start from the acidic solution because you have the acid in the flask. So when you add, this is a strong acid, weak base titration. So it will start from like around 1. We don't need to put the values, but then it should have a nice vertical portion, and then it should go like this. So this is the way you need to draw this one. Okay, so you can also add this here to show the volume, that is 16.67, right? So you can here write down volume of the base added, be added in cubic centimeter, and here you can show the pH here. Even you can show the initial pH as 1.0, and this one, that's it, right? This is the way that you can do, right? So this is theory. Yeah? These are very, very theory questions, right? Yeah, the last part, B. The following 2 experiments were carried out at a constant temperature using the volatile liquids C and D. So I will erase this part for the moment to draw the picture for the part B. Right, let's draw it. So experiment 1, C and D liquids were introduced to an evacuated rigid container. Okay. Allowed to reach equilibrium. When the system is at equilibrium, it was observed that mole fraction of CD in the liquid phase were 0.3 and 0.7. Okay. Here XC is sorry. Sorry again. So C is 0.3 Here XD in the liquid phase is 0.7. And they have given the total pressure PT is 2.7 10 to the power 4 Pascal. So that's it. In experiment 2, again C and D there. So again they say here XC is 0.6 and XD is 0.4 and the total pressure is given as 2.4 10 to the power 4 Pascal. That's it. Give the relationship between the partial pressure of C in the vapor phase, its saturated vapor pressure P naught C, and its mole fraction in the liquid phase X in the form of an equation. This equation takes a commonly used physical law. Write the name of the law. So they say, write down PC in terms of P naught C times XC in the liquid phase. So if you think this as XC in the liquid phase, you denote these things first. XC is in the liquid phase, so then you write down this one. So this is the equation and this law is Raoult's law, right? This is Raoult's law. Calculate the saturated vapor pressure of C and D. So now total pressure is given. In order to calculate the pressure in C here, PC, we have not given any information about P naught C or either P naught D. So we have to think about a different style. What we can do here. What you can do here is, because they are asking the saturated vapor pressure, we need to find that one. So the only thing that I can get here is they have given the mole fraction of the liquid phase and the total pressure. So if I write here, the total pressure PT should be equal to PC plus PD, right? In both cases, right? So here PT, that is 2.7 10 to the power 4 should be equal to PC. For PC, I can write down P naught C XC, that is 0.3, plus for PD, I can write down P naught D times 0.7. And in the same way, for this system also, I can write down. So 2.4 10 to the power minus 10 to the power minus 4 should be equal to P naught C 0.6 plus P naught D 0.4. P naught C and P naught D will not be changed because those are saturated vapor pressures. Okay, so at this temperature, it will not change. So how can I calculate P naught C and P naught D now? I can take this equation as 1 and this equation as 2. And you can see here now this is a type of a simultaneous equation. Now it's O levels. What you have to do, you have to find this, solve this equation and find this P naught C and P naught D. The easiest way is you see here, this is 0.3 PC, this is 0.6 PC. So you can multiply this by 2. You can multiply this equation by 2. And then this will be 0.6 PC, this will be 1.4 PD, this will be 0.4 PD, and this will be twice means 5.4. So 5.4 minus 2.4 is 3.4 into 10 to the power minus 4. And this one to this one minus is cancelling out. 1.4 minus 0.4 is 1.4 minus 0.4 is 1 times P naught D. So automatically I will find P naught D. So if you know P naught D, If you know P naught D, you can find automatically P naught C by plugging into one of these equations. Okay, so this is very simple. Or either if you know P naught D, you can either plug into here or here to find the equation of P naught D, then find P naught D. Because if P naught D is there, you have plugged here. So 3.4 into 10 to the power 4 Pascal times 0.7 plus 0.3 PC equal to 2.7 into 10 to the power 4. So you will find P naught C as well. So when you find P naught C, you will see it will be around 2 into 10 to the power 4. So I have found that one as well, Pascal. This is also Pascal. So this is the way that you can find the saturated vapor pressures. Don't forget, we have done similar type of question in 2018 as well. So you see here, these are very similar, 18 to 19, 19 to 20, also very much similar, so not different. Calculate the mole fraction of C and D in the vapor phase of experiment 1. So you know here now the P naught C is known, P naught D is known in both cases. Now what you have to do, you know the total pressure, you know the saturated vapor pressure, you know the mole fraction here. So the first thing that you can do is you can find PC here, PC. So I will write down this as PC1, PD1, here PC2, PD2, in order to understand. Okay, so my PC1 will be equal to the mole fraction here according to Dalton's law. Okay, according to Dalton's law, mole fraction here XC1, I will take here this as XC1, this as XC2, something like, then for here D, XD1 and XD2. So XC1, PT, what is PT? 2.7 10 to the power 4. Okay, now this is according to Dalton's law. In the same way, if I write down according to Raoult's law, PC1 would be equal to XC in the liquid media, that is 0.3, times the saturated vapor pressure that we have found now is 2 into 10 to the power 4 Pascal. So the only thing that I don't know here, because I can equalize this equation and this equation, 1 and 2 is equal. So then I will calculate XC1. Okay, and my XC1 in the experiment, where is that? Yeah, it would be 0.2, around 0.2. This will be around 0.2. So if that is 0.2, surely my XD1 will be 0.8, because sum of the two mole fraction should be equal to 1. In the same way, I can put here in the experiment 2 the same equations like this, and I can find mole fraction of in the other one is like XC2 is 0.5, and I would find XD2 as 0.5. Okay, so that is the way to calculate. So these are the things that they have told to calculate. And the last question, show the composition of the liquid and vapor phases L1, L2, V1, V2, and the relevant pressures in the above experiment on a pressure composition trace diagram. So you know we have drawn this type of diagram. So you have to draw this one. You have to show the axis pressure in, you have to give this here in Pascal because they have all given in Pascal. And here you need to write down mole fraction. And based on your denote, because here they have given XC, so you can take XC experiment 1, XP experiment 2. So based on how you write, okay, you can write here as XC is equal to 0 to XC is equal to 1. So in the other way around, xd will be equal to 1 and xd will be equal to 0 in this axis. Okay, then you can think about the values and you can draw, because they have given show the composition of the vapor phases, liquid and vapor phases. So L1 and L2, V1 and V2. This is what they have given us to find. Okay, so you know the mole fractions. So in the liquid phase, you know Xc is 0.3. In the vapor phase, you know Xc is 0.2 in the experiment 1. In the experiment 2, Xd is 0.7. This is 0.8. Okay, so based on that, you can just first initially think about, now here if Xd is 1, what you can do? You can write down here P naught D. And this side Xc is 1, so you can draw P naught C. So P naught D and P naught C, the vapor phase should be a straight line, because they are telling to draw liquid and vapor phases. So the vapor phases should be like this. Okay, and what is the, for the P naught C, the vapor phase, you have to write down the fractions here. For vapor phase, for experiment 1, Xc is 0.2. So C is 1 here, C is 0 here. Okay, this is C. So around this region, 0.2 region, I can mark here for this Xc1. Okay, use your notations here as given here. And this is for Xc1. And in the same way, Xd1 here is like, so D1 is around, here it is Xd1, Xd is 1, so it will be around 0.2 as well. So like, okay. And then in the same way, in this is experiment 1, Xc is Xc in the vapor phase is 0.2, and you can also draw to show the liquid phase. So if you remember about our fractional distillation, so basically what is going to happen, you heat it and then you go to the vapor phase diagram. Okay, so when you heat it, you go it, then you condense at the same temperature. So in the same way, we have to draw here, right? So you heat it and then you go to a certain point, then you vaporize it, then you come down. So it will go like this, and at the same time, it will condense, vaporize, and it will condense. So the other system will be like that and come down. Okay. So please don't draw here temperature composition diagrams. They are expecting you to only draw the pressure diagrams. Okay. Then if you clearly understood the mole fractions and here, so you heat it, you condense it, then you have it. So initially you see here, Xc is 0.3 in the liquid phase. And in the vapor phase, Xc is 0.2, which means in the vapor phase, there is a little lower amount. And in the same way, Xd in the vapor phase is higher than Xd in the liquid phase. So based on that, when you draw the curves, the top will be a linear curve, the bottom will be a curved arrow. And based on the composition, you will see this will be a liquid phase and this will be a vapor phase. Because you should note that when you draw up and join this section, and then you condense this section, then you go down. Based on the two values, you will understand which value is my liquid phase. For an example, if I draw that very big, in a very big amount like this, so this one should be this one should be this one. Okay, so if this is my XC is equal to 1, this is XC is equal to 0. Okay, so you see here XC, so this is experiment 1, this is also experiment 1, right? So my liquid phase is 0.3. So here my 0.3 is around here, for an example. And here this is 0.2. XC, right? XC, yeah, here it is here. Sorry, yeah. XC is 0.2 is here. XC 0.3 is here. And in the same way, in experiment 1 for D, so D is 0.7 in the liquid phase. So here it will be 0.7 and it will be 0.8 here. Now think, this is my two curves that could become as in the same way. Okay, this should be the curves. Okay, so what I have to do here is I increase the temperature. Okay, then I do the condensation by dropping the temperature. So here I increase the temperature. Here I do the condensation at the same temperature. I mean liquid to vapor, vapor to liquid composition is there. And when you lower the temperature again, it will form the liquefied solution. So here 0.2 is XC1 and here 0.3 is XC in the liquid medium. Okay, so the liquid composition is changed into a vapor composition. So 0.3 is changed into 0.2, then you decrease. So surely this composition would be the vapor phase. That's my idea. That is what you have to understand. This is the vapor phase, this is the liquid phase. Because for some, the liquid is greater, so some, the vapor is greater. So here you see here, in both cases, liquid 0.3, liquid 0.7, vapor 0.2, but D is 0.7. It's a bit higher now. For D is more evaporating. That is why I have put here P0 D is higher and P0 D is lower here. So that's the way that you need to understand this question. And in the similar way, you need to think about the graph in the same diagram for XD and XC for experiment number 2. Okay, because XC here is 0.6, and when you calculate here, XC here is 0.5, and XC here is 0.4, and X2 here is 0.5. Okay, that is how you can get a clear picture. And if I show you this final result, so it will be very easy for you. So X4, X6 is the volume composition. So you can say, without drawing it separately, you can show it like this. If I share again the original scheme. So you see here, the 0.2 is the V1 composition. This is the volume composition of the vapor phase. And this is the liquid composition of the liquid phase. And these are the mole fraction at different cases. So see here, when you draw, you need to draw the axis, give the mole fractions, units, and the curves. So here they have taken the other way around. Like I have taken PD here and PC here. They have taken PD here and PC here. No problem. The only thing that you need to know is this PDPC curve will be a single straight line. This will be curve. Why? Because when you consider the composition values, you will automatically see this will be a straight line and this will be a curved line. So students have this question, why this is curved, then this is straight line. The reason for that is this is a straight line. When you plug the values for this mole fractions for the L1 and L2, and then V1 and V2, you will see one is going through a straight line, the other one will be a curve factor. That's the idea. Okay. Right. So that's it. We have discussed all the parts, I would guess. Yeah, it's a big discussion with the both structured essay and essay. So question number 1, 2, 3, 4. Yeah, 5 is done, 6 okay, 7 is okay, yes, 8, 9, 10, yeah. Right, so everything is okay now. So please go through this paper very slowly and you will get a lot of information again. And this is 2019, so I will be uploading the 2020 as well very shortly. So you can watch those two, and it will be the end of our discussion then. So see you next time, okay?